And welcome everyone for today's webinar on our new Gurobi version 12.0. So I will be starting with introducing our new documentation, which is a major thing for us because it looks much nicer, as you can see, as the old one. It is really completely revamped. It is based on Sphinx and hosted on Read the Docs. Looks much more modern, has a much better structure and has more cross-references in it. And when you look here at the bottom example, then you see that all of our examples are now for all of the different APIs and languages that you can use in these tabs. So you can just select the language that you want, and then it will automatically always display you the example in your programming language. It's also much easier to maintain for us, and that means we have now the means to do really continuous integration of fixes and also improvements on this online docs almost instantaneously when we find something. So this is really nice, and I hope that you will also find that much better than the old documentation. So please enjoy. So this is on docs.gurobi.com. Okay, and then let's talk about, of course, one of the most important aspects of every new major release that we create, the performance improvements. So here's the usual table that we always provide. There are the different problem classes on the left-hand side, and then the first column is what we call the overall speedup. So this is measured on our test sets and looking at those models for which the slower of the two versions compared, in that case Gurobi 11 and Gurobi 12, takes at least 1 second to run. So everything else where both versions are faster, we consider those problems trivial and not interesting for that comparison. And then the right-hand side column is the set of what we call the harder models, which are those where the slower of the two versions takes at least 100 seconds. And you see here that we have some nice improvements on LP, in particular also for the dual simplex algorithm. Then there is a modest improvement on quadratic programming. There's a quite nice improvement on second-order cone programming, which is actually real. The issue with QP and SOCP is that we don't have that many really hard problems. So in our test set, so this is why we cannot give a performance improvement number for the harder models and on these two sets. And then, of course, the most important set is the mixed integer programming, so linear programming one, where we got an 18.9% improvement on the harder models on our test set. So we will go through them a little bit, starting with the linear programming piece. And I will tell you just a few things, ingredients that we added that improved that particular performance here. So one thing I'd like to point out is one nice additional pre-solve reduction, which sounds a bit obvious, but is not so easy to implement. So this is what we call the derived variables pre-solve reduction. So if you consider a problem which contains one variable y that does not appear in the objective function, and all of the constraints in which y appears are these constraints depicted here. So with the AI transpose x plus and then diy smaller or equal to bi, so y has one coefficient here and that, and then there are multiple variables x involved in that constraint, and then there are multiple of these constraints in which y appears. But now let's assume that for every assignment of x, so given that x has finite bounds, for every assignment of x, we always can find a feasible value for y that would satisfy all of these constraints. It could be a different value for every x assignment, but there is one. Then we can remove y and all of these constraints from the problem and just solve the problem for x. And then after having solved the problem and find an optimal solution to x, we can just calculate the value of y. So that makes the problem smaller, and this works for LP and also for MIP. And we see that for LP, this particular reduction gives us a 0.3% of performance improvement. And on those models where this actually applies, which is not all models, but just a subset, it gives us a 3% performance improvement on the across overall models, so larger than 1 second runtime. And then the very small additional improvement, which gives the same performance benefit, is just a tweak to the aggregator, which is to stop it a little earlier for LP. Okay, then there are more improvements that we made, which I will not go in detail here for the simplex algorithm. So in the primal, we improved the numerics in the ratio test. And overall, you can see here on that slide that numerical aspects, this is really the critical piece for the simplex algorithm that we improved in the Gurobi 12 release. And if you improve numerics in the simplex algorithm, then typically you also get performance out of it. Good, and then there's the barrier algorithm. There are the performance improvements mainly come from, on the one hand side, the pre-solve improvements, but then also for the barrier itself. One thing is crossover is always important in barrier, so that's again then simplex. There we would factorize now more often. That gives a small performance improvement. We have now a better way of handling dense blocks in A, so this is just a data structure thing that makes it faster to. And then one thing that we added is now sometimes if the model has a corresponding structure, we would first in the first iterations we would actually apply just an iterative linear system solver rather than the Cholesky factorization. This is much faster than the full Cholesky factorization, but it is of course also less accurate. But in the end, it helps on this set of models to do that, and then only then after a while we switch back to the Cholesky factorization. And on the set of affected models, that gives almost 10%. So if you have such a model, that can become much faster, but it doesn't apply to many models. Okay, going now to the second order cone programming. That is, of course, also the barrier algorithm, and the pieces that I mentioned before at least apply to this as well sometimes. So here we have three improvements that I want to mention. The one is that we added, actually this is kind of a thing that is a little stupid because we didn't do it, so it was stupid that we didn't do it before. It is just really the trivial piece that if you have a linear constraint that y is equal to a times x, so this is a Doubleton linear equality constraint, then of course you can substitute y for a times x and get rid of y, even if y appears in cones. Then the cone will still stay a cone if a is, if it's just a times x. We do that now, and this gives some nice performance. So, and then also for SOCP, we improved the dense column handling. And we now finally implemented stuff that is already well known in the literature, namely an implicit handling of upper bounds for the cone variables. Previously, we would have explicitly introduced new unbounded variables and put the equality constraints in the linear constraints to deal with that. And now we don't do that anymore, and this gives good performance improvement. Okay, let's talk about mixed integer linear programming now. And here I won't go in much detail because you see here the list is very long, and this is not exhaustive. As always, performance improvements for mixed integer linear programming come from a large number of individual small improvements. So like say pre-solve, there we have, I looked into our Git log files and I found 22 individual performance improvements that did something in pre-solve. And together, we estimate that the pre-solve improvements got 4.3%. Actually, this time, and this is kind of a little bit special, the simplex improvements that we did, these numerical and performance improvements, they contributed the most performance improvement for mixed integer programming. So this was really nice. So my colleague Roland, who was working on the simplex algorithm, was really happy about that. Okay, and then there are, of course, the usual things. So cutting planes, we improved some. So in particular, we included a new type of cutting plane that we call the dual implied bound cuts. That gives a little bit of performance, no pre-solve. And then parallelism, we come to that a little later. And primary heuristics, we also improved a bit there. And with that, I will just show you the historical slide of our speedup. So if you compare the individual Gurobi versions since version 1.1, which was the first version that we released that could solve mixed integer linear programs, we have now in that particular test set with this par 10 metric, 91 times speed up to this version 1. And you see over time, our speed up is quite nice from each version to the next. Okay, let's talk about non-convex mixed integer quadratic constraint programming. Where we again see a pretty nice improvement. So 27.7% overall with 68.5% on the harder models. And when we look at the list of individual improvements, then it's pretty much similar to mixed integer linear programming in the sense that there are already quite a large number of individual improvements that we made that then add up. One thing is the node pre-solve. So we did something that reduced cost fixing now works a little bit better with quadratic constraints. And this alone already gave 10% on this non-convex MIQCP test set. And then some pre-solve reductions. So in particular, we finally managed to add a quadratic aggregation. So that means if you have a quadratic constraint, now we can also use quadratic constraints in the aggregator. So let's say y is equal to x squared. You can use that, and we employ that. This helps a lot for the non-convex models, but it also helps a bit for convex quadratic programs. No, it does not, because it cannot be, because there is an equality constraint involved. Sorry. So equality constraints with quadratics are, of course, always non-convex. Okay, anyway, we improved a little bit the spatial branching value, but this is really just a small, really small tweak, so nothing really spectacular. And we are using now more strong branching in spatial branching, which also gave a little bit of performance here. Okay, moving forward to this slide here that shows again this historic speed up that you get. And this is really nice because it's basically the same speed up as for mixed integer linear programming. The difference is just that this starts only with version 9, which was the first version where we could actually solve non-convex quadratic problems to global optimality. So in just a very short time, we improved it by a very large factor. Of course, you could say that version 9.0 was a little bit crappy, and that's the reason, but that's not the case. Version 9.0 was already pretty nice and competitive compared to other solvers that were able to solve non-convex problems. Okay, and finally, I'd like to talk a little bit about our IIS algorithm. So this is for the irreducible infeasible subsystem finder. When you have an infeasible problem, you want to find a subsystem that is still infeasible, but such that whenever you remove one additional constraint or one additional bound from that subsystem, that then the problem becomes feasible. So this is called an irreducible infeasible subsystem. And now in the algorithm, the fundamental operation that we use when we want to reduce the number of constraints in this infeasible subsystem is we would just try to remove one constraint or a set of constraints and then solve the resulting submap. And if this resulting submap is still infeasible, yeah, then that's good, because we have now a smaller infeasible subsystem, and then we repeat until we can no longer remove anything, and then this is irreducible. Okay, but now there is of course you have various strategies on which subset you want to try to remove, because when it is feasible, then this was kind of a failure and you have just wasted time. So you want to be clever here in that regard. And now comes a very simple observation that is to do with disconnected components. Namely, if you look at such a model here depicted down below, where the model disconnects into multiple individual components, 1 through k, then of course such a problem is infeasible if and only if at least one of these individual components is infeasible. And so that means the irreducible infeasible subsystem will just have constraints and bounds from just one component, because otherwise you could remove everything from the other components and that would still be infeasible. So now the thing is, you can just, if you have an infeasible component, you can just discard everything else from the infeasible subsystem and be much smaller pretty soon. So this is what we do. We exploit now these disconnected components. And we try to find, we go through the components and try to find one that is infeasible. And if we found one that is infeasible, we can just discard everything else. And the algorithm is very simple. It tries the smallest components first, but then it would apply some node limit for these components solves, or for these submap solves, because we want to avoid this very bad case then that can sometimes happen, that there is a small component, but that is really still very difficult to decide whether it is feasible or infeasible, and then it would run quite a long time. While on the other hand, in the same problem, there could be a much larger component where infeasibility is trivial to detect. And so we want to avoid the case that we spend a lot of time in that small component without kind of identifying the larger component to be infeasible. So for that reason, we apply a node limit here. Okay, and then when you have that, then you can get even smarter, because you can then make the regular IIS search strategy to try to produce disconnected components, right? Because the IIS algorithm will, over time, discard rows. And by discarding rows, you may introduce disconnects into your problem. So what we do is we find a separator in the row intersection graph. So that will identify us a hopefully small set of rows that if we are able to remove them, the problem falls apart into disconnected components. And so we just try what happens if we remove it. And if we are lucky and can remove this set of rows, and the problem is still infeasible, yeah, then we are at this nice situation that we now have an infeasible problem with disconnected components, and then we can apply the first idea to just look for the smallest of those. And then finally, another related improvement, but also applicable if there are no components, is this neighborhood definition. So when we are solving a subproblem where we have only removed one row, one constraint, and find out that this subproblem is then feasible, so no longer infeasible, then it is clear that this one row needs to be in our resulting infeasible subsystem. So this would be what we call then a definite row. And now when we already have some definite rows, we can try to look at the neighborhood of these rows. So the neighbor of a row is a row that has a common variable in it. And so we build this neighborhood of these rows in a best breadth first search way until the subproblem is of the kind of nice size, not too large, not too small. And then we try to solve this problem. So we solve kind of a problem around the already definite IIS rows. And if we are lucky, then this is still infeasible, and then we have reduced the problem again. And this will sometimes automatically zoom in on the small components, because if it's almost disconnected and has only a few variables that connect it to the other almost disconnected components, then this neighborhood search will automatically stay within this almost disconnected component. Okay, that's about performance. And now we come to our new features. So we have our primary feature here is that Gurobi 12 is now really able to solve mixed integer nonlinear programming problems to global optimality, which Gurobi 11 was still able to do, but I will tell you what the big difference here is. So first, the algorithmic part. So if you want to solve mixed integer nonlinear programs to global optimality, what you need, at least with our technology, is you need to have an outer approximation in order to construct an LP relaxation. So of course you can also use some other relaxation, but we use a linear programming relaxation. And then when you apply spatial branch and bound, which you need to be able to resolve the nonlinear constraint violations, then you need to have a way to adapt your constraints to the local bounds of the search tree nodes. And this is what we call adaptive constraints in order to tighten the LP relaxation. This is all you need. Then you have an algorithm that is able to solve MINLPs to global optimality, at least if you have finite bounds and you don't run into this undecidability problems and so forth. And then there are optional components. So of course, pre-solve is always an important optional component, and OBBT, so optimization-based bound tightening, is another one, and cutting planes you want to add, and node pre-solve, and of course primary heuristics to find feasible solutions. So this is going to make the solver better and faster. Okay, but let's only look at the outer approximation and the adaptive constraints. I'd like to just explain a little bit how this works. So this is not new. This is already like that in Gurobi 11, but still to set the context. let's go a little bit over that. So we have that linear constraint here. This means all the points that are on this blue line and the sine curve here, those are the feasible points. And we have an outer approximation, which is a convex, linear convex hull here around that line. So we draw some tangents, and that's it in the lower and upper bounds of this x variable. And now let's say we branch on that x variable, and our bounds get tighter. And now the task of this dynamic outer approximation is it should automatically adapt the linear programming relaxation of that constraint so that it now in that subtree node, or however we get the improved bounds, it looks like that. So tighter relaxation. So this is what Gurobi is doing then all the time during the tree search. Okay, let's compare that what we had before. So nonlinear constraints had been initially integrated into Gurobi 9.0. From an API point of view, you were already able to state nonlinear programs with these specific methods here, so exponents, logarithms, sine, cosine, tangents, and power functions and polynomials. And over time, we have added a few more, like logistic function, for example. But with Gurobi 9 and Gurobi 10, you couldn't actually solve this to global optimality. You can also only say that Gurobi should automatically approximate this by a piecewise linear approximation and then solve the corresponding piecewise linear model to optimality, which is of course not the same as your nonlinear problem. With Gurobi 11, you can now actually solve this to global optimality, but still you have to define it just using these univariate simple constraints. And now the big thing in Gurobi 12 is that you can also now state more general nonlinear constraints, so with multiple variables and with a compound structure, so like multiple nonlinear expressions one inside each other. This is what you really want. And this is now done by Gurobi 12. So, and I will go a little bit more into detail of what this means in practice and what the difference is. So here is an example of a nonlinear constraint that you may want to state. And with Gurobi 11, what you would need to do is you would need to break that into pieces. So you have to say that there is an auxiliary variable u that is equal to 1 plus x squared, and then there's the auxiliary variable v that should be equal to then the square root of u, and so forth. So there's this auxiliary variable w, and then there's the auxiliary variable z that you have to explicitly introduce, that is the logarithm of the w. And then in the end, your constraint becomes just w is equal to x plus z, and then z is equal to the logarithm of w, and so forth. And the final constraint will then just be v plus z is smaller or equal to 2. So this is your constraint. But you have to introduce all these auxiliary variables. And that is, in theory, not a problem, but in practice it is, because there is this concept of feasibility tolerances, which is a pretty major distraction for mixed integer nonlinear programs, because they are usually numerically pretty nasty. Okay, let's see what happens if we can only solve these linear constraints and nonlinear constraints and quadratic constraints with a feasibility tolerance of epsilon. Then, namely, this left-hand side set of constraints that you would need to introduce with Gurobi 11 is no longer equivalent to the right-hand side actual linear constraint that you wanted to model with the feasibility tolerance. I give you an example. So this is that one. So here's the y is equal to x divided by sine of x. Well, that's actually a pretty nice nonlinear constraint that behaves very nicely. But of course, the problem is the division here, 0 divided by 0, when you have x equals 0. And this gives rise to a large number of numerical challenges here, which you can see here. So on the left-hand side, there is a potential solution. It's very close to 0, but not equal to 0. But this is at least up to the digits that you see here is perfectly correct. And now let's say due to our feasibility tolerance, we are now able to introduce a small error into one of the constraints, and that makes us the solution change, that u is no longer the left-hand side value, but is a slightly different one that is away from the actual value by 10 to the minus 6. So this is allowed in terms of our feasibility tolerances. And this, when you then follow that through the remaining constraints, gives you a v and a y that is much different. So that this 10 to the minus 6 tolerance in the one constraint that turned into a 10 to the minus 2 violation in the actual composite constraint that you wanted to model. And this is unavoidable because this is just the nature of the beast, that every constraint has that feasibility tolerance, and so the combination can just be different. Okay, and this is now resolved with Gurobi 12, because with Gurobi 12 you can just state the constraint as is, and that means also that Gurobi is able to control this feasibility tolerance on the compound constraint and can then reject a solution that would be feasible in the disaggregated space but not feasible with respect to feasibility tolerance in the original aggregated space. Okay, how do you enter such a problem into Gurobi 12? So there are multiple ways that are supported. So our preferred way is you use Gurobi Pi, so our Python modeling API. This comes with the matrix-friendly algebraic modeling layer, which I will show you in a minute. But then there are other options, third-party modeling tools that have already adopted Gurobi 12. So with Ample and GAMS and JUMP, you can now state these constraints and they will directly call the Gurobi 12 API to model it like that. And probably there will be additional vendors who may also add support for Gurobi 12 nonlinear constraints later. But then if you're not using Python or any of these third-party modeling tools, then you can of course still address that with your programming language, but then the API is a little bit more clumsy because then it is a more low-level error. An array-like form. It's possible, not so nice. Okay, so let's move on to the Python code. So now with Gurobi 12, Gurobi Pi comes with a new NL expression object. And this is to capture, of course, nonlinear expressions. So in this example, you add 3 variables as usual, x, y, and z. And then when you look at these examples, so there is, of course, still the linear expression, the first one that is as before, and the quadratic one is as well. But now the third one, that is now already a nonlinear expression because it involves products of 3 variables. This would, yes. And then the fourth one is also a nonlinear expression because it involves the division of 2 variables. And you can state them by the new add gen constr NL function, which says that the first argument is a single variable, and that should be equal to whatever expression is passed into the second argument. Or you can just use the add constr method with this overloaded equals equals operator, where you also have to put the resultant variable at the left-hand side and the expression at the right-hand side. So this works. So this only supports equality constraints. So inequality constraints are not supported in Gurobi because of some API decisions that we made. And it also only supports the syntax that the resultant variable needs to be on the left-hand side without anything else. So the first thing here, if you want to have an inequality, that can be easily resolved by just introducing an explicit slack variable and then state it as an equality constraint. That's fine. And the second one, yeah, in that case, you just divide by 2 and there you go. Okay, looking at a more challenging example so that you can see how this works in practice and also see some nice additional things that it can do with the Gurobi Pi API. We are looking now at an AC optimal power flow problem. So this is a problem that arises in the energy industry. Whether what type of problem this is doesn't matter for this presentation here. I will just go to the syntax of how you enter these problems. But all of what you see here on this slide is really not really relevant. On the left-hand side, you define some arrays, some constants, and some constants that we need later to express our constraints and variables using NumPy. And on the right-hand side, then you move on with the Gurobi stuff, which is, of course, you start creating an environment and creating a problem as usual. And in that example, you now create four sets of matrix variables, in that case, vector variables, with 4 entries each, because the n is 4. So PQ, and then small d, and the theta variables we define, and then we set the objective as usual. So this is not yet nothing new here. This you can do with older versions as well. The new part comes now in the statements of the constraints. Here we use the addGenConstr NL function. So capital P is now the resultant variable, and the constraint that you see in the comment here on top is the one that we want to define for every I. And we can actually do that with a single matrix constraint using NumPy broadcasting. And this is really nice to be able to state it so concisely. So the main trick here is that one. So the theta you may recall that is a matrix variable with a 1/4 shape. And then theta minus theta dot transform, that is then just a NumPy way of broadcasting, of getting a 4/4 matrix out of that, where each element is theta I minus theta j. Of course, then on the diagonal, you will have zeros. And on the off-diagonals, you have the corresponding differences between the thetas. And then you plug that one into the nlfunc.cosine method, and that gives you a matrix expression with each, in each entry of the matrix, you have the cosine of the corresponding theta difference. And then you would multiply that with the star product here. So this means element-wise multiplication with the matrix G. This is the one where a 4/4 matrix with constants in it. So that means it would just apply these constants to each of the entries in the matrix. And then there's the add symbol that gives you the vector matrix multiplication of our variable V. And then in total, because that is a matrix constraint, you get 4 individual constraints for each I that we have in our P vector. So this is how you would state, or how you can use the matrix-friendly API to state these nonlinear constraints in a very concise way. Okay, let's look at performance and solution quality of Gurobi 12 with respect to mixed-integer nonlinear programming problems. So we have applied now 3 different versions, so to say, of these nonlinear programs that we have in our test set. So when we take our test set, which is typically stated in the compound way, in order to be able to solve this with Gurobi version 11, we have to introduce manually these auxiliary variables and split them, disaggregate them into these individual constraints. So this is using now the so-called, what you call function constraints that we have already in Gurobi 11. And then we can solve this disaggregated problem with Gurobi 11 in red, and we can also solve it with Gurobi 12 in blue, just this disaggregated model. But of course, with Gurobi 12, we also have the option of leaving the problem as is in its compound form, and that gives another way of solving these problems. So now, when you look at the first graph here, this is now comparing the final maximum violation that you get for your original compound problem. Of course, as I have explained before, disaggregating that using these feasibility tolerances can then introduce a much larger violation in the actual compound constraints, because Gurobi doesn't see that that you actually want to solve this compound constraint, because you have to enter it in the disaggregated form. So for the disaggregated form, everything is fine, but for the compound original form, you may get big violations, and you see that here in the red bars that actually there are quite a number of models. For example, 43 models that have at least 10 to the minus 3 maximum violation in these constraints. If you just replace that by Gurobi 12, but still using the same kind of stupid disaggregated model, then these violations already get reduced. This is because of just numerical improvements in our algorithms. But the real thing comes when you now use the actual compound model and use the green bars here to really put the more useful problem into Gurobi. And with Gurobi 12, you can solve that. And here you see that there's, in this test set, not a single model that has a final violation of larger than 10 to the minus 3. So this is really a big improvement. And then when you look at the performance of this, then you can see that Gurobi 11 and Gurobi 12 applied to the univariate models, to the disaggregate models, is basically the same speed. But when you solve the compound models, then it gets faster. So on the harder problems, larger than 10-second models, you get a 62% performance improvement by using the compound formulation. Okay, that's it what I wanted to say about nonlinear. Let's talk about some more minor features that we added to Gurobi. This is a longer list, where I will not go into too much detail. So one thing is callbacks. So we did quite a bit of to improve the usage of callbacks. So one thing is now when you are using the compute server, then with Gurobi 12 you are also now able to pass user heuristic solutions from your callback function to the compute server solving process. For example, you have a problem where you're using lazy constraints. Gurobi passes to you some solution. You find a lazy constraint that is violated. You add that as usual, but then maybe you can also turn that infeasible solution for which a lazy constraint was violated into an actual feasible solution because you know what your problem is, and then pass that feasible solution also to Gurobi. So that should help the solution process then. This was previously not possible in a compute server environment, only when you run Gurobi locally. Now this is also possible in compute server runs. And then for multi-objective callback, that was a feature that was heavily requested by our users, that we are now able to pass additional information to that multi-objective callback. So that means this callback is called after every single individual objective function submap solve. And then you can query information about that submap solve. So like how long did it take to optimize that particular objective function? What was the work? What was the iteration count, node count if it was a MIP? And what was dual bound and MIP gap and stuff like that. So this you can now all query for each individual objective function in your callback. And then we added what we call the callback settable parameters. So some of the termination criteria defining parameters you can now also set inside your callback. So this makes it easy to create a custom termination criterion. For example, you say, yeah, I want to run at most 30 minutes, but once I have found a feasible solution, then I would like to run only for at most 5 minutes. So that means in the callback, you can then set the time limit parameter to 5 minutes. We have enhanced our tuning tool a little bit, so you can now restrict the tuning to a specified set of parameters. So for example, you have already, you know already that that the model is very sensitive to cutting planes, but everything else doesn't matter. So then you just say, okay, just tune on the cuts parameters that Gurobi has. And then the tuning tool will only use that and keep the remaining ones at default values or at the values that you have specified as fixed parameters. And you can now also tune multi-objective models using the tuning tool. Okay, and then there are a lot of additional features that I list here on the slide. So the objective bound attribute is now available also for LPs, similar to the bar pi attribute. You can, in place, in memory, convert a model into a fixed model, so into a model with fixed integer variables. You have the ability to anonymize all of your data files, not only the MPS or LP files, but also attribute files, so MIP start files. By just setting the ignore names parameter, then you would produce a MPS attribute and MIP start files that kind of match in terms of their variable names. So this was missing before. We have now support for a new compression library, which is the XZ compression library. We have added a few things to our logging to improve, in particular, our customer support. And Gurobi Pi now is able to do asynchronous optimization. So, and finally, I like to point out a few improvements that we made regarding hardware resource management, which of course is about memory and CPU. So first one is memory. So we are now a little bit more careful with small and repetitive memory allocation. So we have removed quite a number of malloc calls from the code, because that, in particular on Windows, would often lead to memory fragmentation, and then you are hitting your memory limit or run out of memory, even though the total amount of memory is not large, but due to the fragmentation, you cannot allocate any more memory. So, and also this gave a small performance improvement for hard MIP models by just exercising the operating system memory management not so often. So when you are having a problem with with many variables, and you are also interested in storing many solutions in your solution pool, then you would benefit from our change into the data structures for storing the solution pool, namely when it is useful in terms of memory consumption. If the solutions are very sparse, then we would now store the solutions in the solution pool as sparse vectors. And this gives you a 1.4% performance improvement overall on the hard MIP models when you are setting the pool search mode to 2, so that means an exhaustive search for all solutions, and you are setting pool solutions to 1000, so that means you want to have many solutions. In that case, just storing it sparse way, so keeping the memory low is also helpful for performance. And you also see that in our tests with the previous version, we had 46 models where the memory limit was actually hit. And now there's no more any model with memory limit hit in this test, but for the 46 of them turned into 35 time limit hits, which of course is a little nicer than hitting the memory. And then we have added attributes for you to query the current memory consumption. So you can do that in the callback, but you can also do that after the optimization, querying what is the current amount of memory used and what was the maximum amount of memory used in that environment. Regarding the CPU, we have done a few things. So one thing is we are now a little bit better in exploiting the multiple cores at the root node, because we are now running submip heuristics with multiple threads, in addition to the already existing parallel root cut loops. And that gave us, on our machines, which have just 4 cores, give us a 0.4% performance improvement overall. And the more interesting one is, I would say, that we are now a bit better in the MIP search tree parallelization. Namely, the MIP strategy is, parallelization strategy is that it would go off and every thread would solve some nodes in parallel, independently of each other, and then they would synchronize again, send all the data back to kind of the global data structures, and then a new share of load is then distributed to the threads and so on. And at every sync point, the solver has to wait until all of the threads are done with their work, and it could be that the threads are then running a very heavy long submip heuristic. And then all the other threads have to wait for that one thread to finish that submip heuristic. And now we have introduced the concept of preemption. So the submip heuristic can now be preempted so that the thread can go back into the synchronization, and then after the synchronization point, resume the submip solve. And that helps a lot for very specific problems. And overall, it gives a 1.4% performance improvement. So that was nice. And then finally, we have also done something in terms of resource management for our compute server and cluster manager tools. And with this, I will hand over to my colleague Fernando, who will explain to you what the thread-based load balancing is about. Fernando, please.
Yep. Hello, everyone. So I would like to share with you the most important updates that we have for the remote services in Gurobi 12. And the first thing that I want to show you is the thread-based load balancing. So this new feature improves the distribution of threads across cluster nodes, and this ensures that with this, we ensure that the concurrent jobs use only the available computational resources efficiently without overloading any node. So this means that we are now able to limit the threads that we want to run in each of the nodes, and this will lead that every job that we want to run will need to reserve these threads. And with this reservation, we can balance and we can limit the resources that we have on the node. And in order to do that, we have in the remote server configuration two new properties. The first one is the node thread limit. The node thread limit will be used to limit the total number of threads allowed to run concurrently on the server simultaneously. That means that if you set a number in this specific property, you are not going to be able to reserve more threads that you have set up here. And we also have a new property which is called the fixed node thread limit. The fixed node thread limit will indicate whether or not you want to be allowed as an admin to change the thread limit on a node. So what we can see here in our in these screenshots is just an example of what you will have for the thread limit. If you activate the thread limit in a node or in a cluster, in the cluster manager, you will have two new columns, which is the thread limit and the thread reservation. So as mentioned before, if you set up the configuration property, no thread limit, this is what you will see here, and is the total number that you will be able, the total number of threads that you will be able to use. And the thread reservation is depending on the jobs that you're running, how many threads you want to reserve. So this can be set up either in the bash client or any of the APIs using the dash thread limit for the batch, using thread limit for your environment. So one important thing here is that this thread limit that you are selecting for the job is bound to the environment. So if you define thread limit for 2, these 2 reservation threads will be used when you are running that optimization. And for previous clients that are not running version 12, or if you do not define any thread limit and you have the thread-based load balancing activated, we will auto-calculate the number of threads that the job will be using based on your thread limit and the maximum number of jobs that you set up also in the properties. So a little bit on how this thread-based load balancing works. Well, we are gonna always place jobs where threads are more available, but we also will prioritize nodes with fewer running jobs. In this case, for example, we have 3 different nodes with different limit reservation, limit of the threads and the thread reservation. So you can deduct by of what we have for the capacity on threads that the job requesting a thread limit of 6 will be placed or will be assigned to the node 3. Also, something to mention here is that any job that exceeds all node thread limits are rejected. So if your max thread limit in any of your nodes is less than the one that you are requesting, it will be rejected. Also, a note here is that you don't have to have a cluster. If you just have one node, you can use this to limit the resources on your node. So if you want to set a max number of threads that you want to use on that node, this also can be done. And also another new feature that we have is the job interruption. So with job interruption, you're going to be able to gracefully stop any job instead of aborting. And this will give you some new options that you can perform against this job. So what is the behavior of this job interruption? Well, the optimization will stop gracefully, as I previously mentioned, as if it was a normal stopping condition, for example, the time limit, and then the job remains active. So it's awaiting for further instructions, so you can retrieve solutions or perform operations. This job interruption, it's only available with runtimes from version 12 and up, and it will be ignored in previous version. And this job interruption can be performed via the GRB cluster job interrupt. It can be performed in the cluster manager UI, or even you can interrupt using the APIs that we have for the cluster manager or for the compute server node. And just one final note that I want to share with you in the updates is that we also upgraded to the most up-to-date UI libraries for the cluster manager. So you will have a refreshed UI and, of course, more secure code.